All right, before we jot some things down on page 108, there is a video assignment for tonight, okay, page 111 through 113. We're going to take a look at some derivative shortcuts today. So I really think we're going to like this section. I think it's going to be easy stuff for us, most of it at least. I also want to bring up kind of homework in here. I know on days that I give you a video assignment, that's usually all you do for that evening is view that, that content from the notes. But if I don't give you a video assignment, I'm assuming that you're working on homework from other sections. Is that a fair assumption? Hypothetically fair, okay? So just because reality, no. Okay, thanks for being truthful. Okay, so perhaps in the future, okay, if I don't assign you a video assignment, please try to look at some homework problems from previous sections just to keep it fresh. Okay, we will have time some days in here to do homework, but that doesn't mean you shouldn't try to at least keep it in your head at home. Okay, so please keep that fresh. So for our derivative shortcuts today, in order for us to appreciate the shortcut, I want to first try an example the long way. So, so how have we found a derivative equation, okay, the slope of a tangent line at any point, how have we found a derivative so far this year? What was our definition? Yeah.
The limit h approaches 0.
Yep.
F of x plus h.
Yep.
Minus f of x. All over h.
Perfect. We took some time, okay, in class earlier, well, last week, I guess, to develop where this comes from. Okay, we drew the graph, we plotted some points, we drew tangent line, secant line, okay, we figured out where this comes from. So what I want us to try to do, and it's going to take us some time, is to apply this limit derivative to this function. So if we were to actually write out, okay, what it's going to look like, we'll see. So we got to plug in x plus h for all the x's. We'll see. I'm gonna time you guys. Okay. So this is what we get if we plug in x plus h for all the x's. According to our limit definition for a derivative, we then have to subtract the entire original equation. And all of that is over h. Okay? Now, I'm going to time you guys. This is not a race. If you make it a race, that's your own thing. Okay? But this is not a race. I want to see... Really, Mrs. Bauer, it's a race. Okay, so I want to see how long it would take us. Don't do it just yet. I haven't started the clock. Okay?
Wait.
Hold on.
I'm still writing down. Fine.
Okay?
Fine. I don't
You
better drop your pencil.
Hold on.
What?
I want you to expand the powers. Like, you got to write it three times or 2 times. You got to go through a bunch of FOIL processes, combine like terms, see if anything goes away. All right, it might take us some time. Are we ready?
No.
All right.
Pencil.
Okay. I just finished writing it down.
Okay. On your mark, get set, go. It's not a race. I just want to time you.
I mean, whatever you say, it's not.
When you think you have it, okay, I'll stop the clock, and then I'll see if you're right.
Subtract the original. Really? That exactly?
Wow.
hold on. Let me pause it. What'd you get?
I got 6x squared plus 3x squared minus 12x plus 4.
Nope, keep going.
Go for it, keep it. Come on.
I might have to go for it.
Go for it.
Think we got it?
No.
All right. What'd you get?
3h squared minus 6h plus 4.
You're kind of close.
Oh my goodness.
If you had X's instead of H's, you'd be very close, but not quite. Keep going.
Let's go keep it.
Keep this your mouth shut. That's actually what I got. All my X's canceled out. I just
That's what I was gonna say. Yeah, why'd you all your X's cancel out?
All gone. All my X's are gone.
Yeah, that's what happened to me too. 6x squared plus 3x minus 12x plus 4.
That cancels, I think. That cancels. Me personally, if I put in zeros.
6x squared. Oh wait, that's 4.
God.
Did I not combine?
Think you got it?
Oh, I did not combine.
Hold on. Go ahead.
9x squared minus 12x plus 4.
Yes. All right. 2 minutes and 44 seconds. Some of us are probably still working. That's okay.
Here, fill up on the thing. Show us how you did it.
No.
All right. So 2 minutes and 45 seconds is actually a lot quicker than I thought it was going to happen. In my head, I had like a 10-minute time limit, and if it took more than 10 minutes, I was just going to stop and I was going to put it up there. Okay, so I'm impressed by 2 minutes and 45. But notice how the majority of you are still working. So if you think about the AP exam, okay, for a multiple choice question, you really only have, on average, 2 or 3 minutes per question. Okay, and if this derivative question was on there, 2 minutes and 45 seconds would be a fairly quick time for some, probably not for everyone else. So there has to be some shortcut way for us to figure out a derivative in order to make some of these AP questions go a little quicker. Okay? So in order for us to appreciate the shortcut, I want you to try it the long way. If you were not able to get this, I completely understand why, because there's a lot of algebra throughout the process. But what I want you to do is take a look at the original equation we started with and the derivative that Griffin found us. Can you find a pattern? Do you see a shortcut? No. That's okay. Take a look at the original, take a look at the derivative. Go term for term.
First one's multiplied by 3.
Wait a second.
Alright, first one's
X. I got it.
How can you go from 3x cubed to 9x squared?
You have to
take away the exponent. Oh yeah, you multiply the coefficient by the exponent.
Multiply the coefficient by the exponent, so 3 times 3 would give you 9.
Oh my god.
And then what happens?
Take that one more.
Drop the power by 1, right? Does the same pattern work for the next term? Yeah. Does the same pattern work for the next term?
Yeah.
Yeah. What's going on with the negative 2?
Negative 2 to the 0.
Well, it's like x to the 0, right? Because you don't have x's. So negative 2 times 0 would be 0. Notice how we don't have anything left. There's our shortcut. So what if I did this? What if I changed that 3 to a 7?
21.
Would you really want to go through that derivative limit? No. But can we figure out the derivative faster? Yeah, what would it be? 21x to the 6, and the rest would be the same, right? There's our shortcut. So this is no more. Okay? We have to understand what it represents, okay, what it means, but we're going to use our shortcut from now on to figure out our derivatives. Is that better?
Even on the test?
Even on the test. The rest of the year. Okay? So, on page 109, we're going to take a look at some examples of this derivative shortcut. Now, we kind of already said what happens for the derivative of a constant. Okay? If, like, our equation is 3 or negative 2, like the last number was in the previous example, what's the derivative of a constant? We said that was 0, right? And graphically it should make sense. If you were to graph the equation y equals 3, that would be a horizontal line at the height of 3. And what's the slope of that horizontal line? 0, right? The slope of our line, the tangent line, the slope of that would be 0. So it makes sense. So what we're going to do is try to apply this shortcut that we found to some of these examples. Some of them are going to be simple, some of them are going to get good. What's our derivative? Can we do it real quick? What did we say our kind of pattern was? 6x minus 2. Okay, take the power times the coefficient, and then you got to drop the power by 1. The derivative of a constant, meaning the number on the end, is 0, so you don't have to worry about it. What about the next one? Yep. Perfect. X, yep. Minus 3. Good. Okay. No limit needed. No h's needed. Okay, we're using our shortcut. What about the next one? Derivative of 6. Well, that'd be 0. Well, we'll go in order. I mean, if you want to rearrange the terms, that's okay, but we'll go in order. The derivative of 6 is 0, because that's a constant. So move on to the next term. We'd have negative 9x squared, and then plus 24x cubed. Right? All right? Then they're going to get good. Okay, so now we're throwing in negative powers, but the pattern still holds true. So we got to take power times coefficient, so that would be positive 2. And then if we have to drop the power by 1, it would now be negative 2. Okay, still works even though the power is negative. So the next one would be negative 6x to the negative third. Can we rewrite that derivative equation so that the powers are not negative? Yeah, what would it look like? So you have the idea of flipping it, okay? But this 2 has a positive power of 1. So the 2 actually stays up top and just the x moves to the bottom. Okay, so you have the right idea of flipping. We got to just be careful of what is actually flipped and what's not. So then the next one would be minus, and then the 6 stays up top, and the x to the third would move to the bottom. Okay, if we look at the next one, notice how we're throwing in a fractional power, okay, but it still works the same way. So we need power times coefficient. That'd be 12 over 3, which would be 4. And then if we have to drop the power by 1, what's our new power? Negative 1/3, we say hesitantly. Okay, but that's good. Negative 1/3. And then the next one, or the next term, we'd have negative 8x, drop the power by 1, we got negative 3. Okay, let's change those into power or positive powers. So 4 over x to the 1/3, and then minus 8 over x to the third. Do we like this better than the derivative limit? Yeah, right? Shortcuts are good. Let's try the next one. So power times coefficient, we'd get a positive 3. Drop the power by 1. Negative 3 over 2, or negative 1/2. And then for the next term, 3 times a half would be 3 halves. Drop the power by 1, we'd have negative 1/2. Let's change those negative powers to positive ones, so we can flip the x's down to the bottom. Now for the next term, notice how we already have a 2 in the denominator, so that can stay there, and we'll move the x down with it. We doing okay? Derivative shortcut. We're going to have a few more this year. Okay, this is our first shortcut method. So this process, this pattern that you kind of figured out, is what's known as the power rule, kind of rightfully so, because you take the power and then multiply it by the coefficient. Okay, so we have to have some type of power. So what this notation is telling us to do, okay, we're getting into kind of calculus symbols here. This d over dx stands for take the derivative. So if you were to take the derivative of whatever is inside of those brackets in this case, we want to write what we would have left. So can we apply this power rule to a general x to a power instead of having numbers like we had previously? Can we think about what that would look like in this case? Okay, so the coefficient is 1. Okay, understood 1 in front. So if we took the power times the coefficient, that would be n. Notice how we keep the variable x, like in all the other examples, and then we have to drop the power by 1. So what would that look like? N minus 1. Okay, in general, there's our power rule setup. Okay, but we know how to work with it with numbers, and I'd say that's a little bit more important. Okay, but this is what it is in general. So what we're going to try to do now is amp it up a bit. Notice how these were pretty simple. We threw in negatives, we threw in fractions, but they can get a little confusing. So we're going to try some different ones on the back. Okay, how can we still apply the shortcut rule even though the original function might not be set up properly for us to use it? So in order to use the power rule, we need to have the function look like what's sometimes referred to as polynomial form. That's when we have x to a power. Okay, and if you take a look at all the ones we did on the previous page, they fit that description. There were no parentheses, there were no roots, okay, there were no fractions, nothing like that. So no parentheses, no roots, no fractions. Okay, polynomial form, x to a power. So this, we might have to review something real quick before we tackle some of these other examples. Let's say, for instance, I had a square root. How can I write that in polynomial form? X to a power, yeah.
X to the 1/2.
X to the 1/2, okay? What if I had, for instance, the 5th root of x to the 4th? Yeah? X to the 4/5. Okay, so if you look at the connection, notice how the power on the x is what the numerator represents, and then the root is what the denominator represents. So any root you have is going to have that fractional power. Okay, we have to recognize both parts. All right, so our goal for these other ones is to try to look like a polynomial form, x to a power. So the first one, if you look at the first term, it's a fraction. Okay, there is an x to a power in it, but we don't want it written as a fraction. So how can we rewrite the first term so it's x to a power? And that's it. If we don't want the x in the denominator, we want to move it up, so there's no longer a fraction, yeah? To the -2, all right? So you're used to moving negative powers to the bottom to make them positive. But now we might have to work the other way so that we can write it in polynomial form. Okay, so you're used to having positive powers, but now sometimes they might have to be negative in order to use the shortcut. The next term is already in polynomial form, so we leave it. Notice how I labeled this as f of x. This is still the original function. Okay, we didn't use our power rule shortcut just yet. So this is the same original function, just rewritten. Now that everything's in polynomial form, let's go ahead and find the derivative. Okay, apply our shortcut. Let's see, we get -4x to the -3rd minus 12x squared. Now here's the thing, you can leave it like that. Okay, that's perfectly all right. Sometimes though, if it's a multiple choice question, this might not be one of the solutions, okay, given to you for you to choose from. So what we're going to need to practice is rewriting this in different ways so that we can recognize which one it actually would be if it was a multiple choice question. So something we could do now that we have the derivative we're searching for, maybe we want to change this negative power back to a positive one. So we can move the x to the -3rd back to the bottom and get something like that. So either one of these is acceptable, okay, but just be clear or just be aware that a multiple choice answer might not look like this. Okay, it could look like this, and they mean the same thing. Do we understand that? Okay, let's try the one to the right because it's another fraction, kind of similar to this one. how can we rewrite the original so that we just have x's to powers? Okay, no fractions, no parentheses, no roots. Is there something we can do? What do you think, Christian?
Take out an x on the top and then cancel them out.
Okay, so we can probably factor. All right, so we're left with 3x cubed minus 3x minus 2. Okay, something else just to be aware of is maybe, for instance, this last term did not have an x in it. Okay, you would not be able to factor, but you still could break up the fraction since you're dividing by one thing. Okay, you can divide each one individually. You'd still get the same answer, but just be aware that if the x wasn't there, that was a different method you could have used. So if this is how the original equation can be rewritten, let's go ahead and apply the derivative now that everything's in polynomial form. So I'm thinking we're getting pretty quick with this. It would be 9x squared minus 3. Yeah? Because the derivative of negative 2 is 0. It's a constant. All right. What about the next one? It's not in polynomial form. We want x's to powers. So how can we get rid of these parentheses? FOIL, or a bunch of multiplication. All right, so I don't care the order in which you do multiply. Maybe we'll multiply the first two together. We'll get x squared plus 2x plus 3x would be 5x, and then plus 6. So you can FOIL the first two, but then you have to take that answer and multiply it by 2x plus 1. So we still have more multiplication to do. And then after you multiply everything together, maybe you can combine some like terms. Does that look good so far? Check my math, is that what you have? Okay, this is the original function. We didn't do any derivative yet. So now that everything's in polynomial form, let's use our shortcut. 6x squared plus 16x plus 17. Yep.
And then 5x times 2x equals 10x squared, not 7.
Did I miss it? Oh, I added those, right? So this would be 10. Good catch. So then this would be 11.
22x.
Does that look better?
Yeah.
Yeah. So then it'd be 22 for the derivative. Was that the only one?
Yeah.
Okay. Good catch, guys. All right. Let's try the next one. Okay. No fraction, no root, no parentheses. So kind of similar to the one that we did above, maybe you want to pull out some x's to see if they would cancel, or we can go through this like individual division as we break up each term. Okay, either way you want to tackle it. So x cubed divided by x to the 5th, we'd have x squared, but that's left on the bottom of a fraction, so we want to bring it up to make it x to a power. Kind of similar for the next one. We'd have minus 5, but then x squared over x to the 5th would be an x to the 3rd on the bottom. We want to bring it up and make it x to a power. Okay, no fractions, no roots, no parentheses. So if this is how we can rewrite the original, let's check out the derivative. So real quick, negative 2x to the negative 3rd plus 15x to the negative 4th. Can we rewrite it just in case this was not the solution on a multiple choice? What, or how else could it look? Yep. Good. Love it. Okay, so you can rewrite it different ways. We're doing okay so far? Okay. Let's check out the next one. So, kind of confusing because now we're throwing in a root. let's go ahead and change this root to a polynomial. So instead of the cubed root of x squared, we can write that as x to the 2/3. Okay, so we got rid of the root part, but notice how we still have a fraction. Okay, we want to get rid of that fraction. We want some type of x to a power. So how can we get rid of that fraction? If you have x to the first divided by x to the 2/3, what would we be left with? X to the 1/3, good. Now that would be up top because 1 is bigger than 2/3, so you're left with a little 1/3 in the top of the fraction. So this is how the original function can be rewritten. Let's go ahead and take the derivative. So power rule, we'd get 1x, drop the power by 1, and we'll get negative 2/3. But we can rewrite that to make the power positive again. Okay, move it to the bottom. Is there another way we can continue to rewrite this one, just in case those two were not on a multiple choice? What do you think, Anush? The cubed root of x squared. Yep, so since you have a fractional power, you can convert it back to a root if you want to or if you have to. Okay, so all three of those are correct. They just look different depending on how you want to rewrite it. All right, I want you guys to try the last one. It's already in polynomial form, which is great, but take the derivative and rewrite it some ways to see if we can check out what some of the answers might look like if it was a multiple choice. Let's see, that's what I got as the initial derivative. Does that look right? Yeah? How can we rewrite it? Can we change negative powers to positive ones? Let's see, we can move the x to the bottom, make it a positive 1/4. And then same thing with the other x. You can keep the 2 in the bottom because that's already there from the fraction. So there's one way you can rewrite it. Can we rewrite it another way? What do you think, Anush?
Change the x to like 1/4 to 14.
Okay, so if it's a fractional power, we can convert it to a root if we wanted to. So this would be the 4th root of x, okay, with a power of 1 on the inside. And then the same thing for the other one. This would be the 4th root of x cubed. Okay, all three of these are the correct derivative. They just look different. We doing okay? We're going to stop there for today. All right. Tonight on the video assignment, we're going to take a look at some more, or 2 other derivative shortcuts, but they're going to be related to trig. Okay, they're not that bad, just like the power rule is today.